This podcast was produced from a webinar. For a more interactive experience with visuals, visit advancedmanufacturing.org/webinars.
Hello, everyone, and welcome to another SME Media webinar. I'm Rachel Thomas, editor here at SME Media. Today, we'll explore the topic using computer vision and edge AI for defect detection. This presentation is sponsored by TDK SensEI, and we're joined here today by Sundeep Ahluwalia, Chief Product Officer here at TDK SensEI.
Thank you, Rachel, and thank you to the SME organization for hosting this webinar. Really appreciate it. Hello, everyone. Good morning, good afternoon, good evening, depending on where you are. So my name is Sundeep Ahluwalia. I'm the Chief Product Officer with the TDK SensEI. I have been here since the August of 2024. In my role, I oversee product strategy and roadmap, complete portfolio of our product that includes hardware, sensors, gateway, AWS cloud instance, and then our AI and agentic flow work as well. I have over 30 years experience, started off as a software engineer, and then moved into product management and business development and sales as well. I've been in industrial IoT and heavy industries for over 10 years, having worked in different type of products and markets. In the last 8 years or so, I've been working a lot on computer vision, bringing worker safety to heavy industries, as well as production line optimizations using computer vision. So have a lot of experience in this. I'm really happy to be here and talk to you, everyone here. Next. A little bit about TDK. This cassette tape always brings back good memories for me. For those of you who were born kind of before 80s, probably have good memories of putting in a pencil and reading the tape back in. And for those born after 90s, probably scratching their heads on what is this thing. But this cassette tape actually is very closely linked to the history of TDK. You know, TDK was founded about 91 years ago, based on ferrite, which is an iron-based magnetic core. And that was a very core technology on which TDK was built. And that technology is also in our cassette tapes and the cassette heads that actually read and record play and record the tape as well. And that was the basis on which everything kind of grew in TDK, whether it's the hard drives and other things that use that core technology. But since then, TDK has really expanded into all sorts of components, capacitors, inductors, batteries, and so forth. And I can pretty much say that any electronic device you have today, guaranteed to have a TDK component in it. A little bit about TDK SensEI. TDK SensEI was the first initiative in AI that TDK created. SensEI is a very clever name. In our world, it stands for Sensors with Edge Intelligence. And that's very important because we actually do run our AI models on the edge. In our particular case, we actually run them on the sensors as well. But also Sensei means kind of teacher in Japanese. Kind of speaks to the legacy of our heritage by being part of TDK. TDK, we are TDK SensEI. TDK itself is headquartered in Tokyo, Japan, but TDK SensEI, we are headquartered in Singapore, and we have multiple sites around the world in Tokyo, Japan, in multiple sites in China, and then multiple sites in US, with AI Center of Excellence being in our Pittsburgh office in Pittsburgh, Pennsylvania. And then we also have partners who kind of help take our solutions to markets in Middle East and Europe as well. But coming back to kind of our core product line, we focus on machine health, production line health, and factory health solutions, bringing AI and agentic into this mix. We are right at the cusp of Industry 4.0, which was really all about digitization. But with AI, we are moving into 5.0, which is more about kind of man and machine interaction. And that's exactly where we want to be. So we have a world-class team of AI experts And then, of course, we are backed by TDK. Now, moving on to the main topic here is edgeRX vision. Today, I will cover what solutions are out there and what might be the gaps with those solutions, what is TDK SensEI's approach to computer vision, and then conclude with a actual case study with the ROI outcome as well. So computer vision actually is very prevalent. Most of you probably don't even realize that you use this in your daily life. If you use Face ID to open up your phone, you're using computer vision. I think a lot of people here most likely have doorbell cameras, and if you have that, that's also based on computer vision. It's looking at detection of humans. Sometimes does facial recognition, can differentiate between a package and a live human. So without realizing it, you're actually living in the world of computer vision already. But what I'm going to talk about is going to be very purely focused on defect detection in manufacturing. So moving on to some of the current solutions out there. So there are traditional vision systems, also sometimes known as automated optical inspection systems. They tend to be mostly rule-based, and they work very well. AirSense can work very well if your production line is very simple, and you run one, maybe two product lines. It can be very effective. But if you have a more complex production line, you have multiple different product types, then it doesn't scale as well, and typically you will end up with high overkill. What does overkill mean? Overkill means that you are actually throwing away good parts with bad parts, and that's a loss of really good material that's been thrown away. So everybody wants to make sure that their overkill rate is low. And then you have these big companies that have very expensive, over-engineered applications, but they are very, very slow to adapt, and they're very, one size fit kind of all type of generic, CV solutions. And then there are a lot of tools out there. That's DIY type of tools out there. There's no code. Most of it is on the customer to go create models. The problem with these ones is that they lack full support. Once you buy the tool, you're kind of on your own. And then you also get to this law of diminishing returns very quickly, which is that you'll get to a certain KPI. After that, to improve that KPI is very difficult. And the burden also is on the customers to do that, come up with more data and try to build a new model. It really doesn't work. And those the pain points with these type of solutions is high risk and high cost, major upfront investment, and without even proving the value first. They can be inflexible and very generic. And the real cost is that even with these solutions, you still continue to have disruption in your production line. You still have quality control challenges. And now you are stuck with a sunk investment, which is not paying the dividends you thought it would pay. What is our vision? How do we as TDK SensEI approach this problem? We actually do a custom AI solution, which is based on customer requirements. We tailor our solution to the customer requirements, and especially when customers have a very complex product line, production line, and the defect detection can be very variable. So this is where we come in and really help the customers. We're an all-in-one solution. We provide an end-to-end solution to the customers to address some of their quality control challenges. But we also take a very much a trust building approach, and I'll talk a little bit more about it further, how we do this. It's all about these production lines are running fast, and there's revenue tied to the products that come out. And it's really important that you build trust with the customer as you deploy these solutions. And they're looking for a certain KPI. They're looking for overkill rate to be very low. And this is where we can really be more effective. In the next slide, I'll talk a little bit about our architecture. And, camera placement is very key. So you have to make sure some solutions, when we go into customer sites, already have cameras in place, and there we can be the secondary solution. And I'll talk about that in a slide coming up. But it's very essential that the camera placement be catered towards what exactly you're looking for, and the lighting conditions are really good. So that, I think, something when we come in, when we do a Gemba walk, we take a look at that, make sure that, like, even the existing cameras, if you have to use them, are they the right cameras? Are they at the right speed? Are they focusing on the right product and angle and the lighting conditions? But once the cameras are, assuming cameras are on the right place, the data, the images start flowing in. We actually have a very diverse model, deployment model. We can do everything on-premise as well, and we can do hybrid with something on-premise and on the cloud as well. So why do we need something on-premise? It can be because of latency. Some of these parts, we are going up to 2,000 parts per minute, and you have to make a decision right there and then, and you might be integrated with maybe a PLC system or an MES system in which you need to either stop or start a machine, for example. Then in that particular case, you actually do need to have an edge AI server on the premises to meet some of the latency requirements and to act on any system integrations. In that particular case, we would send image inference and metadata to the cloud so that we can show you all of the events that were captured on the dashboard, where customers can actually go in and validate that event, whether it was a false positive, true positive, and that way, the models then keep improving over time. Some of the use cases that we have worked on, this is not an exhaustive list, but one of them is the inductors, the winding coil inspection. MLCC is the capacitors, where we look about damaged chips and any faulty parts there might be. Wafer inspection, wafers are very sensitive to scratches, and a scratch on a wafer can pretty much lead to bad chips. And before the wafers get cut up and get productized, we want to catch that section and make sure that bad products don't make it out to the field. And then the wire bond visual inspections, you might have a PCB board with the components on it, and you're looking for soldering and wire bonding elements as well. Sometimes the solder isn't very good or incomplete, or a component is missing. So there are many use cases around just this use case as well that we have done and are very good at. We've taken a phased approach, and this goes back to kind of building that trust with the customer, that if they deploy our solution on a live production line, that we have gone through the phases to prove that we can provide the KPI that they are looking for. So first of all, everything starts with data. So say, for example, we're doing a capacitor, we ask the customers to start with, hey, give us a set of good parts, as much as many pictures, images you can give us, please give us that. And then any examples you might have of defective parts, so that we can take that into account as we build our models. And so once we validate the data, label the data, we build our models, we can actually then show the accuracy and feasibility of our solution, saying that, hey, look, given this data set, here's the accuracy that we can demonstrate to you, and here's the baseline performance metrics that we can meet. And this has no bearing on it's not on a live production system, so it doesn't have any impact. But this is the first part of building trust. The second part of building trust is that we will typically go on an actual system, which is offline. It's not in the main production line, but it runs parallel with the production line, and some of the components that go through there will go through here as well. And this is where we can actually show in a live environment, but kind of offline, how well our system performs, and we can actually go back and make optimizations and harden the system even more before we actually deploy it on a primary online system where actual workflow is going in and products are actually going to get shipped. So in these phases, we try to hit the KPIs that the customer wants before we actually deploy it on the live system. So when we go out there, it's with their customers' trust that this solution will work for them, and we go live. So there's two two deployment types you can think of. One is that where you are the primary system. So in many cases, the customers will say, hey, can you bring in cameras and everything else with you? And we can do that depending on the use case and the requirements. We can definitely bring in cameras and stuff for deployment. But the other one where I think we can start very quickly is a secondary use case where they actually already have a system in place, an AOI system in place, but there's still a pretty large overkill, as I spoke in a few slides earlier, that where they still have a good chunk of good parts that get thrown away with the bad parts, primarily because customers sometimes become very conservative. They never want to ship a defective part to a customer, so they rather kind of throw away the good part because of a false positive than take a risk. And this is where we come in and say, okay, let me, whenever you find a false positive or a bad part, let us take a look at that image. And if the part is good, then we can start the machine. If the part is bad, then we can have someone come and remove that part from being taped, for example. So, so this has zero production risk. It's with enough data, we can probably provide very high KPI. We can improve that overkill rate. Even if the KPI is very high for the customers, even if it's like a 2 to 3% overkill, there can still be millions of parts. So if we can recover, and what we found is mostly 2/3 of the parts that get thrown away are actually good parts. If we can recover even half of that, that's a pretty big upside ROI for that customer. So there's really good reasons for us to be a secondary solution as well, where an existing solution already is in place. Next, I'm going to talk a little bit about the case study that we did. This is an actual customer where we actually did a proof of concept, and now we are in commercial deployment with them. It's a leading manufacturer of electronic components. Their main challenges were that they wanted to reduce unnecessary machine downtime. They wanted to improve the defect detection accuracy. They wanted to kind of remove or eliminate the reliance on a manual operator judgment, right? So human judgment can always can sometimes fail as well, and it's not fast enough. So they wanted to minimize that as well, and they also wanted to, of course, prevent any defective parts going into the marketplace. Some of the issues they had, they had inefficient detection with their AI system. They had the 99.5% of all the stops they had were actually false positives, and whenever they had this stop, it actually cost them time because whenever it stopped, in the legacy mode, they would actually have a technician come and take a look at the part, and sometimes, depending on where they were, it could be up to 3 minutes before they could come and evaluate the part and decide whether it was good or bad. And that really meant that the production line was stopped, and there was a delay, and it cost them money, right? So some of the challenges they had, some of the limitations they had, which I talked about very early on with the rules-based AOI systems, is that even minor anomalies that are like dust or your part is not positioned correctly can lead to unnecessary stops, and your algorithms are only as good as kind of your rules-based. So it really gets overwhelmed pretty quickly. But the real reality here is that there is a production loss. And we were on three production lines there, taping lines. And, if you count up all the time, the downtime they had, it was almost 15.9 million units a month that were impacted. And the cost to them was just over 3 lines was $95,000 a month. So it was pretty significant. And, how did we come in and approach it? Ours was a bolt-on, which is the secondary solution. So with this AOI system they already had, whenever it found a defective part or a false positive, it would alert us and send us the image. We would take a look at that image, and if we determined it was a good part, then we would automatically start the machine because we had done the PLC integration with them. So we could take the stop machine, look at the evaluator very quickly, and in a matter of 4 to 5 seconds, we were able to turn that machine back on and get the parts going. So we instantly saved them 2 to 3 minutes right away. And the system itself will archive all the defect images, and it also prevents unauthorized overwrites to make sure that the machine is continually running and not waiting for human intervention. And then overall, we are maximizing their throughput. And I'll go into the next slide of how we approach this problem, right, from a computer vision perspective. So the way we approached the problem, was a multi-stage kind of a AI decision pipeline, and that's very important. Like, this is not just rules-based; this is the actual AI. We get the image, we crop the image down to the exact chip that we want to look at, and then we use some little bit of rules-based logic to look at obvious physical anomalies like damage or debris and things like that, and then try to eliminate those up front. And then we look at the AI model that's been trained on a lot of good parts. So we try to recreate that image of a good part, and if you aren't able to create it, then we know that it is a potential defect. And at that point in time, we move it on to what we call as a classifier. Now, many AOI systems just talk about, hey, good or fail, right? They don't go classify it. We can actually go back in there. We can classify it based on defect patterns, what kind of defect it is, and then reconfirm that, hey, this part, either the part is okay or this part is defective, right? So these are the steps that take some time to design in, but they provide a very high quality of decision making where we can really provide the customer with a very high KPI when we go into deployment mode. And we have actually, the outcome has been fantastic with this customer. If you look at the quantitative results from these just 3 machines, right? We production tested 344 lots, over 180 million chips, out of which, the defective samples that we evaluated were 1,600 approximately. We had 100% defect detection, which means that if a defective part was there, we were able to detect it 100%. And then the false positive stop reduction. So as I mentioned very early on, right, there was a lot of stoppage for false positives, and we were able to reduce that by 80%. And then, of course, we saved a lot of time from 2 to 3 minutes to down to 5 seconds restart of that machine. And it had a real world ROI return. And, just for these, just looking at the 3 lines, if you look at it, we pretty much got them 95,000 of sales, increase in sales. But if you really look at it, all the lines they have, if they were to deploy across all, which we are doing now in the commercial phase, it's almost $500,000 a month of sales gain that were not there before our system was deployed. So this is a proof point where I think when we build solutions that are custom fit for our customers, for their process, for their production line, it leads to a very high ROI return for the customers. And this is kind of where I will say is our USP, is that we don't do a generic solution. We actually build a solution that's targeted for that customer, for that production line. And we are end-to-end. We support them through the whole cycle. And that's a very key part of our solution. And in conclusion, edgeRX Vision, system delivers, measurable ROI returns, as I showed earlier, by reducing the lost production time, by bringing in total quality integrity. And then it is really that our approach to how we solve the problem. It's a product, but it's also a service that we bring to you, and to engage with the customer to really understand the pain points and then address those pain points. So in conclusion, I just want to say that We have a lot of experience in bringing computer vision systems to the market, and would love to have an opportunity to speak with you about your challenges and how we can help. I think that concludes my presentation. Thank you everyone for listening, and we'll open up to any questions.
Yes, thank you so much, Sundeep, for this really insightful presentation. And it looks like we do have some questions to answer. So, just a quick reminder to our audience to get your questions in while we have our expert on hand. So, our first question is, what makes your AI-based AOI different from a traditional rule-based one?
Yeah, so I think the rule-based ones are, you mentioned earlier, they're good for production lines that are straightforward, have one or two different product lines they run on, but they start to fail when the production line gets very complex and is very dynamic. And that's where an AI-based AOI system like ours really thrives. We can handle complexity, we can handle the dynamic nature, we can do the integrations to stop machines or turn on machines, and that's very critical, because when you have a very dynamic environment with, that's where you really truly need an AOI-based AOI system.
Our next question, what does a typical deployment of your of your solution look like? And how long does deployment take?
Good question. So I think it really depends on what the customer wants. But everything always starts with image acquisition. We need images. We need a lot of images to build a very robust AI model. So we need good images of the good, if it's a component, what do the good components look like, and as many images as we can get for what a defective component might look like, or a defective part might look like. That's very important. That's where everything starts. Once we have that, then we can label the data. We can then build those images, build those AI models, and bring it to market. Then the other thing here is about what are the rules of, or what should be, are there any integrations required? For example, do I need to integrate with the PLC system and things like that? So once we have kind of, how customer wants to deploy it, what rules what they want us to do with when we find a false positive, those will lead into how much time it will take for us um, to actually build the right, deploy the right model and the complete solution.
All right, our next question. You mentioned some specific industries you are already in. Is your solution applicable to other industries in manufacturing?
Yeah, so I think computer vision can be very broad. You can apply it, like I'm gonna give some examples earlier, like Face ID and things like that. But we are very focused on manufacturing. So there's some leverage. If we have done, say, for example, worked on inductors and other companies also building inductors, there's some leverage on the algorithms that we can use. But the answer is that universally, we have to adapt to different products, and depending on what the customer is doing. So, there may be some leverage, but typically I'll say that, we really start from scratch in getting the right images for their particular solution. But it doesn't have to take long, really, to show the phase one. As long as we have the images, we can actually produce the result pretty fast, within 2 to 3 weeks.
Okay. Our next question, how does your solution communicate with PLC, MES, and SCADA systems?
Data. Yeah, I think it's really, I mean, we have experience in integration with all these systems. So it really depends on how customers want us to integrate and use their PLC systems, because the PLC systems are very tightly integrated into their own operations. So a lot of the customers will actually not allow you to make any changes to that. So a lot of them will just tell us, hey, we just want you to send us a signal, and we know what to do with the signal. So it just depends on the customer. but we have a lot of experience in this integration. So it's fairly easy for us to do that depending on customer requirements.
All right. Our next question, how much data is needed to train your AI model, and what does the process look like?
Yeah, again, it comes down to the use case. Sometimes we can get away with just a few dozen images. Sometimes when things are very complex or there are many different fault types, then we need more data. Of course, the more data you have, the better your AI algorithm becomes. And of course, once we have deployed, actually, we can even collect more data and continue to improve our models as well. So it really depends on the use case and what we're trying to solve.
Gotcha. Next question, how often does your model require retraining or tuning?
Once our models are deployed, we can look for drift, in the KPI, and if we see that, then we will automatically collect the more data and update the models. So it just really depends on how tightly the model is fit around the use case. Then there are other things that can impact as well, like lighting conditions, for example. A light bulb goes out and then all of a sudden becomes dark. And then customer says, oh, this is, we got a lot of false positives, but because of lighting. There can be many different reasons for why we may need to retune our models. Some dependent on us, some not. So it also depends on if there's new models of the same part coming out, then we may need to retrain. So it just depends on the situation, but typically we monitor. We don't really need to retrain models very often, and we do monitor for drifts.
Gotcha. Okay. Next question is another two-part one. So, how accurate is your detection system/method, and is there a specific hardware limitation in using your solution?
From a hardware, no. I mean, we are we can bring in the right set of cameras if needed, or we can bring in the right set of edge AI server that may be needed depending on latency and customer requirements. I'm not too concerned about hardware side. Typically, we aim for a very high recall, which is that we can detect good parts, 98 to 100% of the time. And then we aim for precision over 95%. In these manufacturing sites, they are they have pretty high KPI demands. So that's what we aim for with our solution.
All right. Next question, what does the pricing/licensing look like for your solution?
So that really, again, it comes down to the use cases and what amount of effort it needs, is how many different type of defects there are, how many product lines we have to look at. So it varies. If people have questions and stuff, we were happy to have a dialogue with our sales team, and get a quote from us. We can come in and take a look at their process and production lines. But it's not something that I think we can. It is fairly, the ROI is there, so I would say that it's not, as long as we meet the ROI, I think pricing is less of a concern.
Gotcha. Okay. Another question we have, what is the maximum speed your solution can handle?
So we can actually handle 100 milliseconds of latency easily. I think in all of these parts, I think the example I gave, they run almost 2,600 parts per minute. So we have to be fairly fast in detecting and alerting. So yeah, I think 100 millisecond latency is very achievable for us.
Okay. A few more questions. This next one, can models be updated without stopping production?
Yeah, the model tuning runs in the background and does not interfere with the production line. And then once the new model, so model update can be done while everything is running. But once the model is ready to be deployed, then we do want to make sure that we inform the customer that there's a new model. So in that case, you may have to have a brief stop so that we can upload the new model and get going. So we wouldn't do it without customers' permission. Do not want to impact any production lines. So we would, at that point in time, we would say, hey, the model is ready to be deployed, and we'll work with them. Maybe it's midnight or something, or when the lines are down or things like that to do that. So that's really, well, that's something we'll work with the customer on.
Next one, can you configure acceptability thresholds in your solution?
The answer is yeah, absolutely. We can provide that capability to our customers as well on the thresholds they want to meet.
Okay. This last one we have right now. How do you envision this technology expanding or changing as companies continue to adopt Industry 4.0?
Yeah, I mean, Industry 4.0 is really an enabler because we do need that connectivity, and the robustness. So definitely Industry 4.0 is an enabler. But I think the key thing here is that our solution is very adaptable, and since we work directly with the customers to understand their production line and the challenges, so we build the solution for them, and they change, we can also adapt our models and changes to fit their needs.
All right. I apologize for the car background. I'm in the office, and yeah, that was heard. All right. Those are all the questions we have to our audience. If there are any other questions, we still have a few moments, so please get them in while we have Sundeep on the line right now. Just give it a few more moments. Sundeep, as we're giving just a couple more moments, is there anything else that you would like to share that you didn't get to touch on during the presentation, or any other tips?
Yeah, I think I'll say reach out to us. If you are looking for a CV solution, or you're dealing with a existing solution but it doesn't meet your needs, we're happy to come in and work with you. Kind of give you our solution and kind of best practices and how to realize more gains. In the end of the day, I think CV, like I mentioned earlier, the use cases, it's fairly straightforward, and it's really how you approach the problem is really where we succeed. So do reach out to us if you have any questions. Email me with your questions if you don't have any here. Happy to connect.
Awesome. All right. Well, I don't see any new questions coming into the Q&A portion, so we'll wrap things up here. Again, thank you, Sundeep and TDK SensEI, for this presentation. It's a very insightful one. I'm sure our audience members really gained some great knowledge from it. And to our audience, our attendees, thank you for tuning in to this webinar, and we do hope that you found it insightful and helpful for your own operations. If you want to stay up to date to any advanced manufacturing news from SME Media and SME the nonprofit, just remember to head to advancedmanufacturing.org for our podcasts, webinars, videos, articles, and everything like that. So thank you, everyone, again. We hope you have a great rest of your day, and take care.
Thanks, Rachel and Sam, and thanks to SME for the opportunity, and thanks everyone for joining.